Hello guys, in today's video we're going to take a quick trip into the world of logic. I know this course is on function analysis, but in order to prove one fundamental theorem in function analysis, I need a concept from logic. So it's important for us to discuss a small theorem or lemma or axiom in logic, and once we understand that, it would help us to prove a very fundamental theorem in all of function analysis, which is the Hahn-Banach theorem. So without further ado, I would like to introduce some concepts in logic, help you understand them. I would not go to the proofs of them because this is not a course on logic, but anyway, it's important for us to know the statements and understand what they imply and what they mean. So let's start with our set X. So set is a collection of elements. And now I want you to remember throughout the process that we are talking about things in a very abstract sense. So it would be very good for your understanding to accept and understand things in their very precise mathematical definition. So I'm going to be very precise in my definition of a set X. So a set is a collection of elements. Now it's said to be partially ordered if there exists a relation on X with the following property. So by a relation less than or equal to, this is, I specify it. It could be anything. It could be less. It could be the sign, say, division or multiplication or addition. So the property that this relation should satisfy is this. So X less than or equal to X, which is the property of reflexivity. I want you to understand very precisely and clearly that I can choose this. So this can be any operation according to my choice, which satisfies these three properties. So X less than or equal to X for every value of X belonging to capital X. And if X is less than or equal to Y and Y is less than or equal to Z, it implies that X is less than or equal to Y, which is transitivity. And then if X is less than or equal to Y and Y is less than or equal to X, it implies that X is equals to Y, which is the property of anti-symmetry. So when I have these three properties on my set X, then my set X is said to be partially ordered. Now, a set is totally ordered if in addition every pair of elements in X are comparable, which means that if X is less than or equal to Y or Y is less than or equal to X for every value of X comma Y belonging to X. So that is what I mean by being totally ordered. Now let me define a few more things and then I would elucidate on these ideas so as to have a better understanding of our intuition. So the next concept we are going to discuss is that of a chain. So a totally ordered subset of a partially ordered set X is called a chain. So it would help us to look at this diagram. So now suppose this is X, which is partially ordered, which means that my set X is a collection of elements such that, so first look at what a chain means. A chain means a totally ordered subset of a partially ordered set X is called a chain. So look at this diagram. So these points are my individual elements, see, and let me say that these are different elements. Okay, now within my partially ordered set there exist chains, which means that these set of elements, let me use a different pen to highlight them. These set of elements, what do I mean by a chain? So a totally ordered subset of a partially ordered set X is called a chain. So this is a partially ordered set, and there are other elements also here. I'm not drawing them as of now, but okay, so there are other elements here also, but not every element is comparable to every other element. You see? So these elements in this yellow strip are all comparable to each other. They can all be compared to each other using this notation, using this relation. But elements in this chain cannot be compared to elements in the chain above it. So that's the property of it, that within a partially ordered set exists a totally ordered subset, and that totally ordered subset is called a chain. So that's the basic concept of what I mean by a chain in my partially ordered set. And so this is a totally ordered set. This is a totally ordered subset. So these two are my totally ordered subset in my partially ordered set. So my partially ordered set X is a collection of all these elements. And elements within a chain, within this subset, can be compared with each other. We can say that A2 is less than A1, and A1, we can say that A2 is greater than A1, or A1 is less than A2 within my chain or within my totally ordered subset. But capital X is my partially ordered set, which means that not every element can be compared with each other. The elements satisfy these three properties. So the elements satisfy these three properties, but not every element is comparable to each other. Whereas in a chain, every element is indeed comparable to each other. Let X be a partially ordered set, which is this, and Y be a subset of X. Let's call it this Y. An element X belonging to capital X is an upper bound for Y if Y is less than or equal to X for all Y belonging to capital Y. So consider these as my Y's, that A1, A2, A3, A4, A5, A6. Now, an upper bound for Y is some X. So there is some X in my capital X. There is some element in my capital X such that I can do this operation, that Y is less than or equal to X for every value of Y belonging to capital Y. So suppose this is my chain. Here is A1, A2, A3, ... And no matter till what extent I take that chain, if I have an element X such that every AI for is less than I belonging to capital I. So if AI is less than or equal to X for every value of I belonging to capital I, then I can say that this X is indeed an upper bound for Y, for all Y belonging to capital Y. Now the element M belonging to X is maximal if M less than or equal to X implies M is equals to X. So now we see the definition of well ordered. So if we do a further, now a totally ordered set is well ordered if every non-empty subset of X has a minimal element. So before we saw that a totally ordered set was an ordered set, a partially ordered set, where every element can be compared with each other with the help of this relation. Now we add a further structure to this set. We say that if I take any non-empty subset, it has to have a minimal element, meaning a element which is less than every element of this set, and this less than is defined like this. So the less than relation is not specifically less than relation. I can define this relation on my own. Now comes the interesting part. Now we have the axiom of choice. This axiom divided mathematics into two parts. One who chose to believe in it went on with proving the Hahn-Banach theorem, and the others who did not, they have their own rules of mathematics. It's called constructive mathematics. They don't believe in the axiom of choice, but the problem is that if you do not believe in the axiom of choice, you are faced with so many difficulties and the whole analysis becomes so difficult. So in order to go ahead with our course in function analysis, we are taking the side of non-constructive mathematics, and we do believe in the axiom of choice. And the basic idea or notion of axiom of choice is as follows. So suppose you have an infinite number of boxes, and I ask you to pick exactly one item out of each box. And so the axiom of choice essentially says that it can be done. There is a rule which can be specified. I may not know it at this point of time, but the very fact that this can be done. What if I have an infinite number of boxes and I want to pick just one element from each of these boxes? So my axiom of choice says that this thing can be done. The famous British philosopher mathematician Bertrand Russell gave a very nice example about the axiom of choice. He said like this: so suppose you have an infinite number of boxes and each of these boxes have a pair of shoes. So if I want to take just one shoe out of that, I can specify a rule explicitly that take the left shoe or take the right shoe. I do not need the axiom of choice in order to do that. But now suppose you have an infinite number of boxes and each box contains a pair of sock. Now when it contains a pair of sock, I cannot specify a definitive rule or a specific rule that take the right one or take the left one, because there is no right sock or left sock. And at this point of time, the axiom of choice comes into picture. It tells me that yes, I can do this thing. I can pick one element or one sock from my infinite number of boxes. I may not know how to do it. It does not give me a specific function. All it says is that yes, it can be done. And once we have this construct in mind, we can prove the equivalent theorems and lemmas. So the Zorns Lemma also says of the same thing, the Well Ordering Theorem. So the Well Ordering Theorem, the Zorns Lemma, and the axiom of choice essentially mean the same thing. That in order to pick one element from an infinite number of boxes, where each of box consists God knows how many elements, the only thing that it says specifically is that yes, I can do that operation. And now if you see at the Zorns Lemma, let us look at the mathematical definition of the axiom of choice, Zorns Lemma, and Well Ordering Theorem. So the axiom of choice says let M be a set of non-empty sets. There is a choice function f on M with f mi belongs to mi for all I belongs to capital I. Now this is exactly what I said. It might not make so much sense what it's written. Now this is exactly what I said. This axiom of choice, this is the mathematical equivalent form of writing the infinite box example. The well ordering theorem says that every non-empty set can be well ordered. Zorns Lemma says that let X be a partially ordered set with the property that each chain in X has an upper bound. It follows that X has a maximum element. Now look at this diagram to understand Zorns Lemma. So I have my partially ordered set and I have all these chains. Now all that Zorns Lemma is telling me is that if every chain has a maximal element, which meaning that the equivalent of maximum element, the maximum number, say to 1, 2, 3, 4, 5, 6, the maximum number is 6. Similarly, we can define a maximal element with the help of this relation. This relation is also arbitrary. This relation should just satisfy these three properties. So with the help of this relation, I define a maximal element in each of my chains. So I have a partially ordered set, and this partially ordered set is composed of different chains, an infinite amount of chains, so as to say, and each of these chains has a maximal element, which implies that the whole of my capital X has a maximal element. So the interesting thing to look about it is, suppose all of this, suppose this A1 is the maximal element of this, B1 is the maximal element of this, C1 is the maximal element of this. Now individually, these elements from these two different chains cannot be compared, but I do have, let us call this the God element. So this God element can be compared with every element in every chain, maximal element. let me summarize it because this one is a tricky concept. So you have different chains, you see. Elements in this chain have a maximal element Ci. It may or may not be possible that these elements are comparable to each other. The elements in different chains may or may not be comparable to each other, but all we know that X is a partially ordered set, and each of these sets and each of these chains has a maximal element. Then we are saying that X itself has a maximal element such that every X is such that M is greater than every X. So that's the equivalent form of the axiom of choice, which is Zorns Lemma. If I believe in the axiom of choice, I can prove Zorns Lemma and the Well Ordering Theorem. If I believe in Zorns Lemma, I can prove the axiom of choice and Well Ordering Theorem, and so far and so forth. And one of the things that we have to make sure that in the axiom of choice is that when I said that there are infinite number of boxes, I do not mean a countable infinity. So you can just say that let's take my infinity to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I am talking about incountable infinities. Good example to understand the difference between countable infinity and that there are different kind of infinities is as follows. So if I give you two circles, now I ask you, tell me the number of points on this circle. This circle has an infinite amount of points, and this circle also has an infinite number of points. But if I draw an arc, the number of points here is less than, of course, the number of points here. So this infinity is less than this infinity. So in terms of infinities also, we have different sorts of infinities. They're countable infinities, they're uncountable infinities. And basically the axiom of choice is not just restrained to countable infinities or to finite sets, because if we have a finite set, then we can use induction to prove our hypothesis. So axiom of choice is applicable for uncountable number of infinities also, which gives it the real power that we would use in proving the Hahn-Banach theorem. And the second thing is that we might not know the concrete definition of this function, choice function. All we are saying is, as such kind of a choice function exists, which can give me one element from an infinite number of boxes. And these infinities can also not just be countable infinities, but any kind of infinity, uncountable, but any kind of infinity. So that brings us to the end of this trip into logic. We'll go back into function analysis in the next video and prove the Hahn-Banach theorem.